Right, hello. Yes, welcome to my YouTube channel. I've built this classic transistor Zener linear power supply or linear regulator. It's a very common linear voltage regulator using transistors. So this is a transistor Zener regulator. Well, you would be wondering why I have to share with you this kind of power supply, which is a very common, well documented power supply. The only thing unusual about this particular one is that this now uses a transistor as a Zener. This is the Zener part of the circuit. There is the input capacitor, and then this one is the output capacitor, and then the transistor, the power transistor there. So the yellow and black is the input DC voltage, and the black and white cable is the output voltage. So this power supply is using a transistor. As you can see there, it's a BD139. That's an NPN transistor as a Zener. Instead of using the Zener, the proper Zener, you are actually using the transistor in a configuration that would give the Zener effect. And yeah, I'll share with you the configuration that you can use for the transistor Zener regulator. So here I have the TIP 41C power transistor, and this one is the BD139 transistor, and this is the resistor, the input to Zener voltage resistor, and then you have an output. Quite a simple circuit, and the Zener voltages for transistors, you actually have a base to emitter in reverse bias. That's the junction, the base emitter junction in reverse bias. That's the Zener effect, because it is a low voltage junction. So as you can see there is the base terminal, right? And the base terminal on this configuration is actually tied to the collector terminal, and the emitter is on its own. So you have this configuration for an NPN transistor. The emitter is actually the positive side, as you can see here. From the resistor, it goes to the emitter terminal, and then it also goes to the base of the power transistor, the TIP41C, right? So you have the base of the BD139 connected together with the collector, and then the emitter is actually the positive sides, and then the base and the collector is actually soldered to the negative, or the common point, right? So that's one configuration. The other configuration, you can actually tie together the collector and the emitter, and then you have a Zener configuration of a bipolar junction transistor. So yeah, let me show you the drawings for the configuration for Zener connection. So here, the first one, this is an NPN transistor. You have this two junction in the transistor. So you have the base, which is here the common point, and then the collector there. So you tie the base to the collector, and then the emitter is on its own, it's a positive. So you have this configuration, which is a reverse biased configuration. So you have that Zener effect here, and every transistor has a different Zener voltage. I think also of the same transistor part, you have different Zener voltages because of the tolerances, right? And then there is the connection for the PNP transistor. You can see here the collector and the base are tied together, and then but the emitter is actually the negative side, so you have this configuration here. So the voltage of the Zener is actually the voltage of the base to emitter, and here on the first one the voltage of the Zener is voltage of the emitter to base, okay, meaning that the emitter is the positive and the base is the negative. Here the base is the positive and the emitter is what? The negative. So that's the PNP connection, NPN connection, right? For the other connection, now the configuration, you tie together the collector and the emitter, thereby you have this junction here. It's basically behaving like a capacitor, but on low voltages and low frequency, it has no effect much. It has no much effect there. You don't even see the effect of that junction, so it's actually ignored. Here it's not in effect because it's actually shorted. Okay, that junction is shorted, but here it's a reverse biased junction, meaning that it is now acting as a capacitor because we have two conductors and an insulator in between, right? So this is another configuration, and the Zener setup is like that. You have the positive here, that's for the NPN. The positive is on the collector emitter tied together, and the base is actually the negative. So you have that reverse bias as a Zener effect. So the voltage of the Zener is called the voltage emitter to base, okay? But the emitter, remember, it's connected together with the collector, right? So here the PNP version, you have actually the collector and the emitter connected together still, and that's the arrangement of the Zener there. The voltage of the Zener is called actually the voltage of the base to emitter, the base being the positive and the emitter being the what? The negative. So these two configurations do work, and you must remember that there is the PNP transistor and the NPN transistor, and you can actually use these configurations. So that's how you can actually use a transistor as a Zener voltage, right? And then there is a list I made here for different which I'm going to share with you on my next voltage regulator, the power supply that I use. You can see that every transistor has got a different Zener voltage. This is the 2SA1046, which has got a 13.6 volts, and then this is the TIP32C, it's a 13.3. So these are the these are the PNP transistors. And then the PNP transistors, okay, 2SC2482 has got that voltage, and then the MJ13009 has got 13.57, and then the BUV26 has got 11.27 voltage. It's plus minus some tolerances, of course, right? So I have not seen I do not have a transistor that I have actually measured that is a voltage that is lower than 6 volts. I have only tested the transistors that I have seen. They start from 8 volts going up to 14 volts. Those are the ranges of the voltages of the emitter to base voltage in reverse bias. Okay, so this is the arrangement. Sorry that it is upside down, so at least I made it that way so that you can actually see the transistors together, compare the Zener voltage. So if you are building a power supply, you select the transistor that will actually give you a voltage within the range that you want, and then you can add the voltage using a normal diode or an LED, like the 11.0 voltage. You actually be within the range of 12 volts if you are building a 12 volt power supply, and then if you are building a 15 volts power supply, you would go for a 13 volt transistor. okay, and within other voltages. So yeah, this is how you can actually use a transistor as a zener, right? So I will now go on to power this circuit and then show you how the voltage will vary. Okay, I'm going to use a power supply. This is the power supply that I'm going to use. So you can see this is 23.3 volts. So I'm going to input 23.3 volts and then measure the output. Right, I have connected now the power supply here. You can see here that's the DC input from the power supply there. That's 23.3 volts, right? And then here I've actually connected the meter. That's the positive on the white and then the negative on the black there. And this is the voltage of the output, 7.96 volts. This is because the BD139 will actually give you around that value. Okay, if you measure the zener voltage of that transistor. Okay, let's try to measure the voltage of the transistor. Okay, so this is the voltage of the transistor here on the emitter. Okay, you can measure the voltage of the transistor. That's the voltage of the transistor there, 8.5. Okay, 8, okay, right. So that's 8.51, meaning that the other voltage 8.51, 7.97, right? If you subtract 8.5, if you subtract 7.97 from 8.5, you will get around 0.6 volts. That's the drop between the base and emitter of the TIP41C. Okay, that base emitter voltage of that transistor there. So that's the normal transistor zener regulator. Okay, yeah. So basically that's how you can actually build a transistor zener regulator. Quite a simple circuit, but very effective. This works normally for low voltage applications. Okay, low voltage, low current applications. But if you are going to need a high voltage input regulation, I'm going to give you another circuit which I'm going to describe on the next video. It's a simple buck converter using transistors. Okay, thank you.